Yeah, welcome everybody, also from my side. As already said, my name is Becker, and I'm working with Siemens. And I do this talk together with Markus, and we actually have a project together, so we work on, this is the project title, the title of today's talk is the project title. So we would like to give you guys a brief update on what we do at Siemens, at the research center Jülich, for runtime profiling and tracing of parallel applications. So the outline of today's talk is pretty much like this. We will quite briefly go through the applications requirements we have at Siemens, and we will also highlight what is the problem we're gonna need to solve. After that, we will review a bit what tool support is needed for that before we go into the details of the tracing system we use, and we call this profiling and tracing system Score-P. As this actually exists for a pretty long time, or with its predecessors exists for a pretty long time, there is already a quite impressive supportive tool stack, and we will review this as well. Of course, we will conclude this talk at the end. I'm pretty happy to announce you the new structure of Siemens again. But you can see here that Siemens is a pretty widespread company. So the application areas of Siemens range from power generation, wind power generation, energy management, building technology, so everything with smart cities, smart star, whatever you want, mobility, interlocking systems, digital factories, process industry, healthcare, and of course, who could live without it, Siemens Financial Services. As can be seen here, we are actually a pretty decent hardware company, but all these products include software. All these products include software that need to be migrated to multicore, distributed systems, whatever you name it, it is correct. So we have this immense code base which was developed for sequential processors, and we have to migrate it to parallel hardware architectures. And just to highlight the problem we are faced with a bit, let's assume you have an application which has already multiple threads. But it's currently running on a sequential processor. But now your procurement department decides, well, let's buy a multi-core, they are cheaper. Or maybe Intel decides we do not sell single-core processors anymore. Both might be true. So what is the experience we have, you have, maybe we all have the same experiences? Once you put this code on the multi-core, what you see first are crashes, latent bugs, non-deterministic behavior. So you see a lot of data races, deadlocks, and so forth. Yeah? So the application does not even work properly. Does this sound familiar to somebody of you? Yes, I see some low-hanging hands, but it seems to be true for more than just us. So what do developers usually do in these cases? They manually, without the help of any tool, look for these bugs. They try to find the places where they crash with some means, and they put a lock around it. A lock and unlock, resulting in a horrible performance. Yeah? You might have heard about these scenarios where somebody tells you, well, I put my code on a multi-core and now the application is 60% slower than on a single core. This happens. This is also true. Yeah? But in real-life scenarios, it's like this. You start with this process. Somebody from the above-the-line people, so the higher-level management, promised to somebody, we will enable multi-core support. But you, as the developer, have to go to this guy, to your manager, and let him know, my program still crashes, and I don't know why. I did a lot of stuff, and now the performance is also horrible, but please give me more money. Yeah? This doesn't work at all. So the bottom line is that a migration from a single core to a multi-core to a heterogeneous system as well is extremely challenging. Yeah? That's why we need tools, right? The individual steps, just to recap them again, you have to perform in order to get from a sequential algorithm to a parallel algorithm. You need to identify first some concurrency, something you actually can parallelize. You cannot parallelize everything. Then you need to decide on how you actually want to program that, on the parallel architecture of it. And there are several ways you can actually program a parallel server pattern pretty wrong. So you need to know this. Yeah? Then you need to do the parallelization. Yeah? And here also, you probably do not want to reinvent the wheel. So there are many libraries at hand you can use. But you can do horrible mistakes by selecting the wrong library. Yeah? Once you did that, nobody is interested in your application so far. You first have to prove that it's correct. Yeah? Which is actually pretty impossible for a parallel program, right? Do you want to prove all interleavings? So even here, for the verification and validation, you need tool support. Yeah? At least helping you, assisting you to some extent with some intelligent algorithms, figuring out, well, there's a data erase or there's no. And at the end, you need to apply again a runtime optimization. You need to do again profiling and tracing in order to figure out where do I lose performance. And in this parallel case, we do not speak about losing a few percentages. We speak about several dozens of percentages, just because you just spread around the logs infinitely. And it isn't interesting how these logs are implemented. They are overhead. You first need to understand where are these logs. Yeah? Of course, you need tool support for that. And in particular, for today's talk, we focus on the profiling and tracing aspects of that. You need them desperately to identify where potential is, where parallelization potential is, and you need it to optimize it at the end. Yeah? And only with these tools you can actually do this quite fast and also correct. So let's sum it up. What is our scenario? Our scenario is that we have tons of code. Nobody understands that code anymore. We call it legacy code, just for a second. You know, legacy code is code where the developer of the code is either retired, dead, promoted to some other position where he doesn't want to look at code anymore, or works for another company. Yeah? So the legacy code is there, nobody understands it, but now you have to parallelize it. Yeah, now you have to do these wise decisions on this needs to run parallel. And this is also correct. And this yields to performance improvement. Yeah? But this is not easy. So the parallel runtime execution behavior is pretty complex, not easy to follow. Yeah? And do you want to, one of the fastest ways probably on getting started is you could start debugging your code. You can do a 10-step continue, and then you realize what your application is doing, but this isn't an option at all, right? I hope we agree on this. So that's why you need to have profiling and tracing. And here it is important, it's really not only about getting it faster. At the very beginning, it's just about understand what your damn code is doing. Understand it, maybe debug it, and maybe reverse engineer it. And just after that, you can even dare to think about performance optimization. Yeah? And interestingly, up till to understand it, forget about performance drawbacks, some overheads of tracing and so forth. You don't know what your application is doing, so just try to get that and then think about the overhead of profiling and tracing. So what would be, in an ideal world, from the Siemens perspective, and I'm talking here from the company perspective, so corporate technology is the department within Siemens which provides actually knowledge to all the different Siemens business units, so we have to focus on all of them. The focus here is clearly on understanding the application. It's not the kernel we want to understand. We want to understand the application in the user space. We want to understand where are the processes, where are the threads, where are the logs, where are the messages. Where are these guys waiting for each other? Where is the synchronization overhead and the communication overhead? Yeah? Of course we want to have it portable, right? We do not want to have it on Linux or only on Windows. Actually, we want to have it portable in a way because then we can also hope to do it on some Siemens proprietary stuff. Yeah? It should be quite hardware independent, so we do not focus on one specific thing. Yeah? And of course, it would be really, really great if it would be also possible to capture something like QDOC cards, Intel Xeon Phis as well. Yeah? And we do not want to do the whole Sunday alone, right? We want to focus here on open source formats, enabling us to use an existing open source tool stack. Yeah? We do not want to do all the UIs ourselves. We do not want to think about all the analysis algorithms ourselves. But we want, that's why we want this open format here for profiling and tracing. So we actually had this situation at Siemens, and then we looked around to the tracing systems out there, and we found one. We found it pretty amazing and interesting. It's actually called Score-P. It's a combined development of the Research Center Jülich, the Technical University Dresden, RWTH Aachen University, the Technical University of Munich, the German Research School for Simulation Sciences, and the University of Oregon. It's funded by the German Ministry for Education and, surprise, the Department of Energy from the US. Actually, this is pretty amazing because it's one of the rare situations where the DOE sends money over the Atlantic to Germany. It is an open source tool, you can download it. It works on Linux, and in the last 6 months, Siemens, so we enabled also a Windows version of it. It is hardware independent, you can run it on x86, ARM and PowerPC. It has CUDA support, and I heard about some prototypes for Intel Xeon Phi which are not yet available. It has an open format, which is used by a bunch of tools, and it's extremely scalable because it comes from the HPC domain. It pretty much fits our needs. It focuses on the parallel application behavior. It provides a real bunch of different instrumentation wrappers from processes, threads, accelerators, source code instrumentation through the compiler, also binary instrumentations, and also manual user instrumentations. Yeah. It has the core, actually, which does all the event handling and filtering and whatever you want. And then there is a bunch of open source and sometimes also commercial tools relying on it. For instance, there is the Scalasca tool set, which is developed by the Research Center Jülich, which automatically searches for patterns of inefficient performance behavior. It has a profile viewer included. On the other hand, we have the Vampire Trace Viewer, which is a commercial tool developed by the Technical University of Dresden, and other tools from the University of Oregon Tau or from TU Munich Periscope. So we thought it would be pretty nice to try this out, how it works, how we can make it suitable for our use case. And at that point, I'd like to hand over to Markus.
Yeah, thanks, Daniel. I'm going to show you a few features of Score-P and the developments we did within our joint projects together with Siemens. So as Daniel already said, all the partners that are involved in the Score-P project all have an HPC background, so high-performance computing, and our target systems most of the time look like this. So this is the supercomputing system we have in Jülich, which has about 28,000 nodes with 16 core processors each. So we're talking about 450,000 cores in total. So we need to develop tools for scalable systems. And Score-P comes with this in mind. So it provides a typical functionality for HPC, which is support for process level parallelism, for the message passing interface, or SHMEM, which in this case doesn't stand for shared memory, but it's a library for remote memory access via one-sided messages. We support thread level parallelism using OpenMP, which is most commonly used in HPC, but recently we also added basic pthread support, and we have support for accelerators, so GPUs programmed in CUDA. Score-P 1.3 is based on instrumentation. Here we support a number of different techniques, and we provide extensive runtime filtering and selective recording capabilities. So you really have many choices to reduce the amount of data that you're capturing, to really focus on the parts that are interesting for your particular application. One key feature of Score-P compared to other performance tools in the HPC world is that it provides a flexible measurement environment with a single recompilation, typically. So that's for getting the instrumentation into the code. Once you've done that, you can generate profiles and traces and even provide online access to the profiling data without recompiling, so all this is configured through environment variables. As Daniel already said, we have a strong focus on scalability, so we're really focusing on these big systems. So we have successful runs, measurements of Score-P at the scale of a couple of 100,000 processes. So it's really high scalability, and it's quite portable to support all the major HPC platforms out there, like the Blue Gene system here, which is PowerPC based, the Cray systems, Fujitsu systems, which are Spark based, Power under AIX, and of course also Linux based clusters with different hardware architectures. As you see, all these features come from the HPC world. And now, within this project with Siemens, we basically try to extend the capabilities in the directions that, that suit Siemens needs, which are more multi-core rather than multi-node applications. I forgot, of course, Score-P is open source, so we release it under a 3-clause BSD license. Okay, so how does the Score-P workflow look like? So you typically start off with your source modules, which you then pass through an instrumenter, typically based on the compiler and linker, so you end up with an instrumented executable, which basically includes the application code plus the measurement library. This is then run in parallel, either as multiple processes or one process with multiple threads. And by default, it generates a profile, a summary report, which is written in the Cube4 profile format. This summary report can then be manipulated by a number of command line tools and can then be viewed in 2 graphical user interfaces. One is Cube and the other one is Tau PowerProf. And with that, you can really dig into the details of the profile of your application. Now, based on this profile report, you can go back and optimize your measurement configuration. You can, for example, apply filters to exclude certain parts of the code from measurement, and focus on the parts that you're interested in. And then you can go on to tracing, and our tracing format is called OTF2, which are written in parallel. You can look at them using a timeline view, using Vampire, a commercial tool, but you can also do a Scalasca trace analysis, which again generates a Cube4 profile, which is enriched with rate state information, and then you can look at this profile again with Cube or PowerPoint. So that's the basic workflow of Score-P. Now let's have a look at the individual points. First, you need to instrument. We provide different ways of instrumentation. One is to do things manually, so we provide an API to instrument phases, functions, arbitrary code regions, and also do measurement control, so turning measurement on or off. But most of the time, people are using automatic instrumentation, using the compiler interfaces, or source-to-source translation, or by linking against pre-instrumented libraries, or by GNU linker symbol renaming. So there are various options here. Within our joint project with Siemens, we developed automatic binary instrumentation based on the Intel PIN tool, which provides a flexible instrumentation at image load time. So we don't do this during compilation, but when we load the image. No recompilation is necessary. Unfortunately, it only supports x86 architectures. The current prototype that we have supports function wrapping, so we can capture all the different functions. We can do pre-runtime filtering, so we don't do it at runtime, but we can control what gets instrumented at image load time. And we can replace the threading API routines for different threading APIs by calls to the measurement system to capture the different APIs. Future work that we want to do here is to support even more like MTAPI or Intel threading building blocks. Now let's have a quick look at the supportive tool stack. As Daniel already mentioned, there are a number of tools sitting on top of Score-P. First, the Cube Profile Viewer, which shows you 3 columns. On the leftmost column, you have a list of the different performance metrics that are captured. When you select one there, you see where the particular metric, how this metric splits across the call tree. So where is it located in the source code? And then when you click on there, on the right-hand side, you can see how this particular metric in this particular call path distributes across the system. In this particular case, we have an application which used 64 MPI ranks and a whole bunch of p-threads. As I said, after profiling, you can switch to tracing. Here we have the Open Trace Format 2, which is a successor format that was of the formats OTF and Epilogue that were used by MPI and Scalasca before. It's very flexible, scalable, because that's what we had in mind, and space efficient. It's a multi-file format, and it supports many different event types targeted to the needs of our application people. It has a well-defined read-write API in C, and Python is on the way, actually. So what can you do with these traces? You can do a timeline visualization of these traces in Vampire. So you see the overall timeline at the top. You see process-specific counter timelines at the bottom. Of course, you can zoom in to get more details and really dig down into the problem. Another alternative approach to this is to do an automatic trace analysis, and that's what we do with the Scalasca project. The idea is here that we automatically search for patterns of inefficient behavior, try to classify and quantify the behavior, and provide a higher level result out of this huge amount of trace data that we have. And the advantages are that it's guaranteed to cover the entire trace, it's quicker than a manual analysis, and we do it using a parallel replay strategy to exploit the available memory and processors to deliver scalability. It does not replace the manual analysis using Vampire, but it complements it. So these tools can really work together. An example of an analysis that we added in the course of our joint project is a log contention analysis, which is a frequent and severe problem during the multi-core migration process. So what we do is to automatically determine the waiting times in acquire log operations. So we try to find out where is my application blocked at a log, and we can also determine which other thread caused this. We do this automatically. And with that information, what actually our future work is, we want to figure out where does it come from. So which operation on thread 1 in this example delayed this process so that thread 0 had to wait in the acquire log. We already have such an analysis running for MPI, and we want to extend it for the multi-threaded paradigms. Our prototype currently supports OpenMP and pthread, mutex, and condition variable APIs. So, to conclude, parallelizing legacy software is a really tedious job, and first of all, developers have to understand all parts of the software, and then they have to get the synchronization right and efficient. The profiling and tracing tools can help the developers to understand their code. Just by looking at a profile generated with Score-P, you already get some insight. Looking at the trace in detail, you get even more how things really interact with each other. The tools have to be portable and extendable, and they should allow to focus on only the relevant parts of the application. So, as you all know, if you're doing tracing, you can easily generate huge amounts of data, and yeah, you really have to be careful here. For Siemens, Score-P fulfilled these requirements, and it comes with a supportive tool stack to enable these kind of migrations. And with that, I'm done, and thanks for your attention.
Any questions?
So you gave an example of a sort of an analysis that you could do on the traces to do a kind of block intention analysis. Is that something that an application programmer could write for themselves, or do you have to be an expert in the tool to write from first?
So the analysis is actually hard-coded in the tool itself. So we have an automatic trace analyzer, and it detects not only this pattern, but a whole bunch of patterns. And yeah, it's basically a code snippet that's part of the analyzer that is executed while replaying the trace to find this situation, to keep track of statistics and such stuff. So how many instances, what was the severity, how was the severity distributed, and things like that. So that's part of our analysis tool.
Other questions? Yeah.
So for the trace formats that you use, I think when I have looked at the state of things when I did the common trace format, it was at version 1 and it was not really doing what we needed. So I see that you're now at version 2 of the trace format. So are there some very specific things that you need in there that would drive it kind of going for a more common format?
So to be honest, today was the first time I learned about the common trace format, and what I heard there was way too generic for our kind of analysis, because it's completely definable, and we need strict semantics for our analysis. You really need to know what these individual events mean to do the analysis.
Yeah, but since you create a trace and then you can feed it to a trace viewer, that trace viewer could expect to have some events and some fields.
Okay, for the viewer, I totally agree. Viewers don't have this strict semantics.
For an analyzer that expects some specific events and fields, it can query and see if the trace contains them or not, and then bail out if it doesn't.
That's not really an approach that our users like, to be honest.
Okay.
Other questions? Comments? Maybe one comment. I mean, you showed many different tools there, but I think a lot of them are proprietary, like PIN from Intel and Empire, and I think a lot of those are proprietary tools, if I'm not mistaken.
In fact, the tools sitting on top of Score-P, except for Vampire, are open source. So Cube, Scalasca, Tau are open source. Vampire is commercial. Score-P itself is also open source. So it's the only commercial tool that sits on top of Score-P. With PIN, you're right. It's free for non-commercial use from what the Intel website states. But it's just one approach of doing the instrumentation. We offer many more. So.
Okay. Okay, thank you.